Hello everyone, my name is Aldrich, and I'm going to present to you our study titled Dynamic Model Merging for Class-Incremental Learning on Imbalanced Ocular Disease Image Dataset. As we know, deep learning models have been pivotal in assisting healthcare by aiding medical image analysis, such as eye disease classification using fundus images. As we see in this chart from past works, the model performs extremely well on these tasks, consistently reaching the 90% mark. However, there's a catch. Did you know AI can have amnesia? Yeah, AI can experience a form of amnesia called catastrophic forgetting. What is catastrophic forgetting? When we train an AI model, it learns patterns from the data we give it, but if we keep training it with new data, like adding new classes, the model often forgets what it has previously learned. For instance, a classifier that knew digits 1 and 2 might forget them progressively after learning 6 and 7. That gradual erasure in old knowledge while learning something new is called catastrophic forgetting. You can see it more clearly in the graph. As performance on new knowledge improves, the old knowledge's performance worsens. To sum it up, when tasked to learn something, the model cannot easily store all of the information as it is prone to lose old info whenever new info is learned. So basically, when we keep training an existing model with new data, it ends up wiping out its memory of what it already knew. To handle that, we need special methods that help the model keeps its existing knowledge while simultaneously recognizing new classes. This special approach is called class-incremental learning, or in short, CIL. Now, instead of retraining models from scratch each time there are new data, this method offers promising solutions by enabling the model to retain knowledge regarding current classes while learning knowledge of new classes. Recent studies suggest dynamic network expansion, such as expanding the feature extractor, can be implemented to achieve better performances. However, this expansion comes in heavier computational overhead since it adds more model parameters when new tasks or classes come in. Yet another alternative is adapter-based continual learning, or in short ACL, not the physical injury, which also uses network expansion. The main detractor though is the parameter increase in each task is not as big as expanding feature extractor, as it utilizes adapter for task-specific knowledge adaptation, and it will be attached to one main pre-trained feature extractor or model backbone. So this is how it works. This adapter will be trained with new data alongside memory replay if it exists in the first step of the training. Next, the adapter will be frozen on the second step of the training, which is the classification head fine-tuning. The problem of this approach surfaces with the downside in the inference phase. In that phase, ACL will switch adapter sequentially, which means if there are 10 tasks, it will change adapters 10 times to find out the result. This is the main cause of this method's computational overhead trade-off. Now, this is where dynamic model merging, or in short Dynamo, comes in, as it offers an efficient solution on the inference phase by merging the adapters into one unified adapter in each stage while still achieving comparable performance to the ACL. Which is when applying for class-incremental learning with memory replay method in medical domains, two sources of imbalances often emerge. Now, firstly, in medical domains, datasets often come in imbalanced distribution, where the more uncommon diseases are underrepresented compared to the more common ones. Now, the second one is the class-incremental learning methods that utilize memory replay, such as Dynamo, encounter another imbalance problem because the memory of past classes or tasks is typically more limited compared to the new classes to be trained. Now, while Dynamo partially addresses this imbalance problem by undersampling the data when it is in the classification head fine-tuning session, it leaves considerable gap in the adapter training stage, or the first step of the training.
Now, covering the goal, what are our main goals for the study? We have two, actually. The first one is going to be to extend the Dynamo implementation in the eye disease classification using fundus images. The second goal of our study is to handle both imbalance problems in the adapter training stage. How do we achieve these two main goals? we're going to be tackling these two main goals, or maybe achieving these two main goals through our methodology. And this is going to be the rough estimation or the rough visualization of our methodology. In short though, first off, starting from the left, we're going to be gathering the dataset. Then we're going to be pre-processing the data into two sets. It's going to be, or two setups. The first setup is going to be the baseline setup, and the second one is going to be our modified setup. And keep in mind, these two setups will be using two different memory sample sizes as well, to see if it's going to increase in terms of performance as the memory size goes up. We're going to be using memory size sample of 25 and also 200 for both of these setups. Then the last step is going to be evaluation, where we're going to be evaluating our model's results using class metrics. To be exact, there's going to be two categories of metrics we're going to be using: class incremental learning metrics and also for class-specific metrics. And this is going to be the main graph or the main visualization of our dataset. We're going to be using the dataset of retinal fundus multi-disease image dataset, or RFMID for short. And if you look at the graph, the data is very imbalanced, you could say. And this is good for our experiment because we want to tackle this exact problem. Now, we're going to be dividing this main dataset into a couple of subsets. And also, this subset was created by choosing the single labeled images and extracting 10 classes chosen based on the amount of data available. Also, to add on top of this, we're going to be separating the 10 classes as previously explained into 5 incremental tasks. So 10 divided by 5, that's going to be 2 new classes introduced incrementally. So 2 by 2 by 2 and so on. And these are going to be the tasks on the right side. In total, it's going to add up to 5 tasks. And here is the exact way we're going to be tackling class imbalance. We're going to be tackling it using our class balance focal loss method, or our formula. Now, we're going to employ this class balance focal loss in adapter training stage, to be exact. And it's also going to introduce 2 main components. The first main component is going to be focal loss, which is going to be using a modulating factor and class weighting to make models focus on the harder samples, which typically do come from less frequent ones. So that's going to be the part where we're going to be tackling imbalance. On the other hand, this is a second factor, or second component, which is going to be effective number of samples. This was introduced as a class weighting method that computes a class's effective sample size to mitigate bias in long-tailed datasets. And this is going to be the configuration we're going to be using for training. For our training configuration overall, all configurations of the hyperparameters are the same in both approaches, except for one, which is the adapter tuning loss, which our method, as shown before, will employ class balance focal loss. Also, we're going to be running approaches in 2 memory constraints, like I have explained earlier. We're going to be using a memory sample size of 25 and also 200. And these are our 2 main categories of metrics: class incremental learning metrics and also class specific metrics. What these 2 are will be covered on the next slide, which is here. Now, to start off with, I'm going to be explaining the class incremental learning metrics. The first one is going to be average accuracy, which will represent a model's capability to retain knowledge over time without significant degradation. The second one is going to be latest accuracy, which will represent the model's final performance. Now moving on to the class-specific metrics. We're going to be using 3 here. The first one is going to be macro average precision. The second one is macro average recall. The third one is going to be macro average F1 score. Macro average precision will measure the model's ability to correctly predict each class, whereas recall will measure the model's ability to correctly predict samples among all actual samples of a class and a dataset. And the last one, which is F1 score. F1 score is just a harmonic mean, or you could say an average for both precision and also recall.
Okay, so let's take a look at the result. Our approach significantly improved the model performance across all metrics in both class-incremental learning metrics and class-specific metrics in limited memory scenarios. Specifically, we achieved around 11% latest accuracy improvement over the baseline, and then around 2% increase in average accuracy, and other improvements in the macro precision, macro recall, and macro effort score. However, it's worth noting that we observed some accuracy drop in task 2 due to prediction challenge. Thankfully, the model recovered in further tasks. This behavior underscores the pivotal role of classification head fine-tuning and highlights the opportunity for further refinement in this area. With larger memory buffers, the performance gap narrows. While the model continues to excel in class-specific metrics, the model performance in class-incremental learning metrics is slightly below the baseline. Also, the accuracy drop observed is less severe compared to the limited memory scenarios. And then, to understand how each component contributes to the model's performance, we conducted an ambitious study on 25 memory samples. And we trained the model with ENS and focal loss separately. The ambitious studies suggest that combining ENS and focal loss gives the best results in majority of the used metrics, which indicates that both approaches are complementary. So in conclusion, we have successfully extended the Dynamo implementation in eye disease classification using fundus images. And we have successfully handled the both imbalanced problem in the adaptive training stage. By integrating simple yet effective modification of the loss function, we see improvement in class-specific metrics, specifically in limited memory buffer. And then, a better study confirms that our approach, which combines the ENS weighting and focal loss, shows the complementary benefit. And for further study, should explore more on improving the second stage of the training, hyperparameter tuning, and different adaptive structure. And so that's all from us. Thanks for watching.